In the last classes, we have already learned about definition of vector spaces. We have also learned about the concept of linear dependence and independence. And we have also looked at the concept of subspaces. In today's lecture, we will try to cover topics on inner product spaces and essentially only the introduction part mostly and some theorems related to inner product spaces. And we'll try to introduce the concept of linear transformations. So these are the two objectives of today's class. So to define inner product spaces, first of all, let's look at what it helps us do. So inner product spaces, once we have defined them, that we'll do in just a minute. So once you define them, you can get the concept of length, how the magnitude that we talk about of a vector. So it helps us define the magnitude of a vector. Not just that, it also helps us define a concept of angle between the vectors. So concept of angle between vectors. That's where it helps. And going by the general definition of vector spaces, not all vector spaces are inner product vector spaces, which also means, which essentially means that you cannot define inner product for all vector spaces. Only a few of them allow that properly. Now, this is the definition of what is an inner product. Okay, so we'll just go through it one by one. The properties required for defining an inner product. So in a real or a complex vector space, an inner product is a scalar function defined as a function which takes one vector, another vector, and does something to them. Okay, we're defining it as a product, so we'll just use this symbol, right? But it does something, some operation between the two, and the resultant is a field. What you get is essentially a field. Of course, you can generalize this concept further beyond the real and complex vector spaces, but the idea is that you take two vectors and you end up getting the field essentially that you had used to define the vector space. So there are different notations that people use. The notations are some places you will find them written as A dot B. Some places they will define inner product as brackets and having the two vectors A, B in the brackets, this fashion, parenthesis. And then you have another way of writing it in using the angled brackets, right? This is another way. Now, since we have been using angled brackets to signify the span, to imply the span of a vector space, so we'll not be using this. We will not use this in this class. Okay, but at places this is the symbol. This is the way you denote inner products. Now the properties that this spatial function that we are calling inner product should satisfy are first is closure, which means this should be for every A and B belonging to vector space V, you would end up getting a field F once you have used this function. So A dot B is always, thus for any vector A and B of vector space V, you will get this property is defined. Associativity is if you scale a vector with the field alpha, then and then take the dot product, is the same as scaling the dot product with alpha once you have taken the inner product, right? So this is associativity with respect to the field F, the scaling with respect to the field F. It also satisfies this property of distributivity, where if you add the two vectors and then take a dot product with the third vector C using this pen, uh, then it is equivalent to taking the dot product with C with individual vectors and then adding the two. Okay. So clearly this addition is vector addition, whereas this addition is scalar or with respect to the field addition. Now, if you use a complex vector space, for complex vector space, it satisfies this conjugate commutativity. The way you will define is, let's say if you write B dot A, then this is not going to be equal to A dot B in general. You will think for real vector spaces, this is true, of course. But for complex vector spaces, this is not true. For complex vector spaces, you have to take a complex conjugate of this. So B dot A is same as A dot B complex conjugate. So it has this conjugate commutativity as the way we'll define it. Now, there's an additional property that comes out. I think this is the last property, which is called positivity. So if you take the same vector from the vector space, A dot A, this has to be greater than or equal to 0. Okay. This cannot be less than 0. This is always positive. So one of the key things that inner product space requires. So what if you end up getting A dot A equal to 0? This implies only one thing, that the vector A is nothing but the 0 vector. So now there are some special subspaces that you would encounter when you would be uh, going through some material linear algebra or during your research. There's something called Hilbert spaces. Hilbert spaces are those vector spaces that allow definition of inner product and norm of the vector space. Then vectors can be defined as in this fashion: is norm is under root of v dot b. Now we know that v dot b is always positive, so we can very safely take an under root. So the norm is a real value. The length of the vector is real. It's never complex, of course. Now, of course, there are other kind of inner product spaces that you may have encountered or you will encounter. They're like, for example, Banach spaces and Sobolev spaces. Now, these kind of vector spaces are mostly used for functions, and they allow certain properties of inner product spaces, again, of a certain kind. So we'll not get into that in this course. But anyway, moving forward, finite dimensional inner product spaces. For example, the examples of finite dimensional product spaces are two-dimensional space, two-dimensional real space, two-dimensional complex space, two-dimensional complex space, three-dimensional real space. So, and then you have infinite dimensional inner product spaces also. What are they? You have already seen them before, the polynomial spaces. So, or or spaces, vector spaces of functions. So, set of all functions which take in real value, and give you a real value. Let's say we are looking at them. This is an example of infinite dimensional space, and those functions should also be integrable. The f square should be integrable. Okay, that's a requirement for it to satisfy the inner product definition. And then the inner product then can be defined as, I've used angle brackets here, but let's say we use parentheses, let's say like this. So f comma g inner product can be defined as an integral. Okay, I've chosen the limits here minus infinity to infinity, but they need not be the same limits. And then you multiply the functions and then integrate them over x over this in this interval. So this forms an infinite dimensional inner product space. Very useful in these kind of things are very useful when you would be dealing with solutions of ODEs and PDEs. So now, of course, you have Euclidean space, which are real inner product spaces, and there's something called unitary space, which is an equivalent of Euclidean space. It's just that it allows complex numbers to be there, so it's called complex inner product space. Right. Then let's look at some theorems. First theorem that we have is Schwarz inequality. Uh, let's say if you take absolute value, take inner product between two vectors u and v, and look at the absolute value, then this has to be less than equal to, that's what the theorem states, the norm of u into norm of v. So that's the theorem. So to prove this theorem, what we'll do is we'll construct, we'll uh, start by choosing a vector of a certain form. It's just a trick that we're using. So let's say we define a vector w in this fashion. So this definition is nothing but essentially saying the vector w is norm of u square into v minus v dot u vector. Now when we take w dot w, we get the, so w dot w, this is the positivity property of the inner product spaces. So w dot w has to be greater than equal to 0. Now let's look at the dot product. So we expand in the expanded form. This equation looks like this. This inequality looks like this. Now we sort of take the dot product. So let's take this term and let's take this term, take the inner product. We'll get norm of u square into norm of u square, giving you norm of u4, norm of u to the power 4, and v dot v gives you norm of v square here. So you get the first term using this term, and this term gives you this term. Correct? Now let's look at the second term, which is let's sort of take inner product with this part and this part. So minus minus becomes plus, v dot u comes from here, and another v dot u comes from there, and you get u dot u as the norm of u square. Now for the third term, let's look at, for example, let's look at this term dotted with this term. Okay, so here you get norm of u square coming from here. This is there, right? We have placed it there, and we get v dot u from here directly, and then this v dotted with this u gives you this v dot u. Okay. The last term we get by taking inner product between this and this part. So you get v dot u into u dot v, u dot v, and norm of u square. And this has to be greater than equal to 0 because it's a positivity property. Now, as you can see, we can cancel off this term with this term right away. And the two terms that we are left with, we can manipulate, do an algebraic manipulation like this. We can pull out norm of u square. And what you're left with is norm of u square into norm of v square minus v dot u into u dot v. Now, let's sort of, before we move further, we have seen this complex commutativity or conjugate commutativity is defined as this way, correct? Now, v dot u, you can say, is same as u dot v complex conjugate, correct? Now, if you take a complex number, let's say this is going to be, let's say, complex number z bar, and this is then z. And when you take, this is just z, and when you take multiply z with z bar, you get norm of z or absolute value of z square, correct? So this sort of brings us here, is what you get. Okay. So now if we take, and this is a positive quantity, so the absolute value of z is always a positive quantity, right? So when you take, so if the squares are satisfying the inequality, then their under roots will also satisfy this inequality, and you get u dot v absolute value has to be less than equal to norm of u into norm of v. So we see that we have proved this theorem shows inequality for both uh, real vector spaces and complex vector spaces. Now let's focus only on the real vector spaces. Of course, you can extend it to complex too, but let's sort of talk about real vector spaces. Then we can write u dot v as -1 to 1. And I'm just writing this thing. So if you have taken u dot v and you're looking at not just the absolute value, but allowing it to, for real vector spaces, you can do that for sure, allowing it to have the negative values too. So it should, this inequality would mean that this u dot v divided by norm of u and norm of v would always lie between the values -1 to 1. Correct? Now, once you know that, you say, oh, I can, most of my trigonometric functions like sine and cos, they have values between -1 and 1. So why don't I do this? I say cos theta is u dot v divided by norm of u into norm of v. As soon as we do relate, define our this quantity as cos theta, we get the concept of angle between two vectors. Of course, this fits really well with our R2 and R3 spaces. We two-dimensional spaces and three-dimensional spaces. We already know exactly. We can relate to it physically, the concept of angles with the dot product. But for n-dimensional spaces also, you can define angles between vectors, which is not very intuitive, but going by this definition, theoretically at least, we can define it. Now, if why cos theta not sin theta? Because we wanted to get to this concept of orthogonality. So now we see that if u dot v is 0, then the cos theta will be 0. That means the angle would be pi by 2. And such vectors which have inner product as 0, we call them as the orthogonal vectors. So this is also sort of coming from our two-dimensional and three-dimensional concept of perpendicular lines or perpendicular vectors, right? So if the angles are perpendicular, then the u dot v is going to be 0, and then your angle between them you say is pi by 2. But for n-dimensional space also, you have generalized the concept here, and you can call n-dimensional vectors also as orthogonal. Although the angle that you want to see may not be clearly immediately become apparent in an n-dimensional space. Correct? Now, having said that, now this also indicates, sort of before we proceed further, some sort of a concept of projection that the u dot v gives. So let's say if this is the angle theta, and you're defining u dot v as, let's say this is u vector and this is, let's say, v vector. Now, if you define cos theta, then you say, if I define it like this, then you can say, think of u dot v as norm of u into norm of v to cos theta. That's the way. And somewhere you can think of it like u being projected on the v vector. So let's say if I modify this a bit, and I can write this as u dot v vector divided by norm of v vector. Let's say define it like this, and this is norm of u into cos of theta. I'll just zoom in. So I'm saying that what we do is, let's say, to take the inner product u dot v, we take u dot v as norm of u into norm of v cos theta, going by this definition. Just we are using simply using that definition. Take this norm of v to the left hand side and write this as u dot v divided by norm of v into, that is equal to norm of u into cos theta, right? So v by norm of v, you can write this as a unit vector. So the length of v divided by norm of v is going to be unit vector, is going to be 1. So we can write this as v hat, let's say. So now u dot v hat is nothing but norm of u into cos of theta. Correct? So now you can see immediately that you can sort of now think of this as u, there was a length of the vector, let's say this is norm of u. Correct? So this was norm of u. And now I'm taking the angle that we define as theta, and the length of this, when I do u dot v, I get something like norm of u into cos of theta. Correct? So you can think of dot products as projections also. Okay, projection of u on v, and similarly you can also get to projection of v on u. It's the same thing. So the inner product can also be seen as projection of one vector onto the other vector. Okay. Now moving forward, let's say we choose this. We're going to extend on this concept of orthogonal vectors. Let's say for an n-dimensional vector space, for n-dimensional vector space, if for representing the vectors, we choose certain spatial vectors, not just randomly picking any vector, but a certain set of vectors which have the following property of being orthogonal to each other. Each of them is orthogonal to the other one, which means that when I take product of any two, ei with ej, where I can take values from 1 to n, and then excluding, and then j can take values from 1 to n, and you take dot product between any two vectors picked from this set, you either get 1 if I equal to j and 0 if I is not equal to j, and which we can sort of this this relation, this equation, we can write it as ei dot ej equal to delta ej. This is just a notation that one uses to represent this kind of property, that if I equal to j, then it's 1. If I is not equal to j, it is 0. And we call this as Kronecker delta. That's a special name given to it. You can also see delta ij in the matrix form as if I equal to j, it's all 1. And if it is not, then they're all zeros. You can, so delta ij can also be seen as a matrix, and which essentially means if you want to look at the equation, this is a matrix equation, correct? So this is just something about the initial notations that people use often, and we will be also using it. So they can think of this as E1 dot E1, E1 dot E2, E1 dot E3, and so on. And here you'll get E2 dot E2. You zoom in. Okay. And then here you have E2 dot E1, and so on. And then this is equal to 1, 1, 1, 1, 0, and so on. Correct? So this equation ei dot ej is equal to delta ij can also be seen as a matrix equation, okay, in the written in the initial notations. Okay. All right. So coming back to the orthogonal basis concept, which means that if we pick such vectors, then uh, we call it an orthogonal basis. Now, if we pick such vectors and try to write any vector from the vector space V in this form, so we say we pick a vector u and then write it as a summation of lambda I ei, and then we pick V also and write it as a summation of mu I ei. Okay, so we have picked two vectors and we have written these two vectors using orthogonal basis. Now, when we do that and when we take the inner product, u comma v or u dot v, whichever notation you prefer, you can write it as lambda I mu I. Okay, this is for real vector spaces. Okay, this particular definition. And if it's not a real vector space, we are talking about complex vector space, and real vector space becomes a sort of a subset of that. Then for complex vector spaces, you have to use this definition where the summation is over lambda I mu I complex conjugate. Now this is important to note. Okay, so for complex vector spaces, you cannot write lambda mu I as the inner product. You'll have to you have to say lambda I mu I complex conjugate. Okay, that's the definition that you will use. We have already discussed this definition. It's just when we apply, it looks like this for orthogonal basis. Okay, and I don't think I need to explain that what is a complex conjugate. If mu I is a complex number with a real part and a complex part, the complex conjugate would be real part minus the complex part. Okay, right? So, right, that's how we define. Now, I think it's easy to see why this happens. If you want me to elaborate, you can think of it as summation lambda I ei dotted with summation lambda j ej. Correct? Now you can write this as summation over I and j lambda I. Oh, sorry, I have been using. Okay, this is v, so we are talking about mu j ej. Okay, this summation is from j equal to 1 to, let's say, n, and this is for I equal to 1 to n, let's say. So this is for n-dimensional space, n-dimensional vector space. Okay, now we'll take the more general example of the inner product between, let's take it as a complex vector space. So the inner product that we'll do, we'll have to take care, like we take the complex conjugate. So now, okay, so let's say this is going to give you lambda I mu j, okay, ei dot ej, okay, and when you're taking dot product, we'll just use this. So we'll just get this summation I summation j lambda I mu j. This is delta ij, and this is summation over j summation of I. Now this double summation is having non-zero values only when I equal to j. So you can reduce it into a single summation, and then you will write it as I equal to 1 to n lambda I mu I power. Okay, this is how you write it. So and that's what we have written here. So this is true only for orthogonal basis. So if you're not using an orthogonal basis, then you cannot take the inner product in this fashion. Okay, you will have more terms because you will have double summation like this. So that you'll have to keep in mind. Okay. All right. Now let's say if you're not given an orthogonal basis, you are given some other basis, and you want to construct out of using that basis an orthogonal basis. Okay. So let's say for a given basis, E1 to En, okay, and of course, this is for an inner product space because we'll use dot product. Whenever we talk about orthogonal, the concept of orthogonality, it is implied that we're talking about inner product spaces. So for a given inner product vector space V for a given basis, you can there would always exist an orthogonal basis which we can write as I1 to In, such that the span of the, and this is not orthogonal, E1 to En, I1 to In is orthogonal. Okay, so that's how we are defining them. Now you can always define an orthogonal basis, this one, in an interesting way, that the span of the first vector E1 is same as I1, the span of I1. Okay, that means they are representing the same, they are spanning the same subspace of the bigger vector space V. Okay. Now, if you take two vectors E1, E2, then I1, I2 will also span the same subspace. Okay. So now the only difference is that E1 dot E2 is not equal to 0, but I1 dot I2 is 0 because this is orthogonal basis. E1, E2 is not. Okay, so with this distinction, but the span, what they are spanning, the subspace they are spanning is the same. Similarly, for any first k vectors to be picked, they have this property now for every k less than n, and it generates the same subspace uk of which is of p. Okay, for every k equal to 1 to n. Okay. Now, to prove this theorem, what we'll do is they will use another method for proving this. We'll call this method proving by construction. So in maths, there are multiple ways of proving it. One is a straightforward way that you prove the statement that has been made in a direct way. You can also prove things by contradiction. That means you say, okay, let's say that this is not true, and then you end up showing that. Uh, Sorry, let's say that something is true, and then you end up showing that it's not true, and the only way it has to be true is that the theorem should be correct. Okay, that's the way you say it. And the third way is proved by construction. You say, okay, this thing, just by existence of this, I can, for any general uh, values, I can just show that it's going to be, it can be constructed. So that's the third way of proving theorems. So we'll use, for this particular thing, we'll use prove by construction. So we'll first start, okay, let's say we define, so we define our first vector I1 as E1 by norm of E1. So we have made it a unit vector. So if it was not a unit vector, it will I1 dot I2 that you will generate later would still be 0. But then you want I1, for an orthogonal basis, you want I1 dot I1 to be equal to 1. Correct? So to this set, now we have sort of constructed I1, and clearly the way, by definition itself, the way we have constructed it, your E1, the span of E1 has to be I1 because it's essentially the same vector but just normalized. Now we want to add another vector such that we want I2 dot I1, this I2 that we are adding to this set is such that I2 dot I1 is 0. For this, let's say we define now, because we want the span of E1, E2 to be same as span of I1, I2, we need to get the components of E2. So we define it as I2 as E2 plus a component from I1 in a way that will take away the component of uh, I1 from E2. That's why we have to, so the way we are defining, we are adding, the way we have to evaluate this coefficient xi to 1 is such that it will take away component uh, of I1 from E2. So let me say that the coefficient xi to 1 will take away the component of I1 from E2. That's how we have to develop this. So what we do is we try to impose this condition of orthogonality on it, on this definition. We take I1 dot I2 of this in this equation. We take I1 dot I2, we set it to 0. The left hand side has become 0, and the right hand side looks like this. Now I1 dot I1 is of course 1. E2 dot I1 is may not be 0. So then to remove the component of I1, we need the condition that xi21 should be equal to minus of E2 dot I1, and that will make sure that I1 and I2 are orthogonal. Now to normalize this I2, you need to now, once you know the value of xi21, you can normalize it. So we find the norm, and the norm has also some interesting properties, that the norm of this E2 plus xi21 is nothing but norm of E2 square minus xi21 whole square, and under root because we're defining the norm. So this is how we get the normalization factor also. Now for the ik thing, I mean, for, like, of course we have shown for 1 and 2, but for general ik vector that you're adding, so let's say by this procedure you have found I2 till ik minus 1, and now you want to find ik. So you have to add ik, so you define ik such that you add the vector ek, and then you have to, from ek you have to subtract the components of I1 to ik minus 1. So we define it as a series like this. And of course, because it has to be normalized, so the normalization factor would be computed this way. Now, to obtain xi k, we say we'll take dot product with any vector ij, which we have already computed. So j runs from 1 to k minus 1. Okay, so it runs from 1 to k minus 1. Then because there I let's say dot with ij is equal to 0 if I is not equal to j, and that's true for every I comma j uh, coming from this, taking values 1 to k minus 1, right? In that case, you end up getting you can directly compute this factor, this coefficient xi kj as minus ek dot ij, correct? So putting it together, now that you have found xi k, so ik looks like this. Now you have to only thing that you have to do is you have to normalize it. To normalize it, you again take dot products like in this fashion. Should add a dot product here between the two vectors, and that will give you ek dot ek. So ek dot ek is here. Then when you take, then you have ek dot summation with this thing. So it's going to be 2 times that for let's say we are dealing with, if we're dealing with real vector spaces, then it's going to be 2 times summation of ek dot ij, because for real vector spaces ij dot ek has to be equal to ek dot ij, correct? Now ek dot ek and plus 2 times this, and plus we'll get dot product between this, and that will be nothing but summation of xi kj square. And the reason is because all the other vectors are orthogonal to each other, so they'll get just the only the when k is equal to j is going to appear here. So yeah, so summation, let's say xi kj ij dot this with itself, with the initial with the let's say we have to run, I should not be using k, wait a second. So let me sort of, just to show this, we'll use this as xi k ij, and this is j, and this is k running from 1, this is j running from 1 to k minus 1, and then you're taking a dot product with summation j running from let's not use j, we'll use m running from 1 to k minus 1. We'll call this xi k m I m, correct? So that's the dot product that we'll take, and then this will reduce to, this entire thing will reduce to something like summation over xi kj into xi km I j dot im, and j running from 1 to k minus 1, and m running from 1 to k minus 1. And then you can, because ij dot im is delta jm, right, is the canonical delta, you'll end up getting something like reducing it to one summation where we can replace j with m. We can equate the two. So we'll get this xi k j, xi k j, and j running from 1 to k minus 1. And that's what gives you this. Okay. Now, if you would look at this quantity, what this is nothing but minus psi k j, right? And this is coming from here, correct? So that's what we've used. So this will become minus times 2 times xi kj square. Now you're adding 1 time and subtracting 2 times. So it will be like subtracting 1 time. And ik will now reduce to something like this. Okay. All right. So we have Now found a way to generate all the vectors from 1 to n like this. So, right, now we'll take an example. Let's say we'll take a four-dimensional space. We have taken a four-dimensional R4 space. Okay, we're taking that four-dimensional space, and we are taking three vectors in it: E1, E2, and E3. And we want to do Gram-Schmidt uh, orthogonalization now. So we can say E1 is in this form, E2 is this, E3 is this. So stepwise, if we go the way we went about constructing the general vectors I1, same way, we say I1 is E1 by norm of E1. Norm of E1 is going to be coming from here, 2 square plus 0 square plus minus 1 square. It's going to be 1. And finally, 1 square, which is this. So you get root of 6. Okay. So the normalized I1 looks like this: 2 by root 6, 0 by root 0, minus 1 by root 6, and this. Now we want to construct the next vector, I2, by adding E2 to this is I2, 1, I1. Correct? That's what we're doing. Now, so your I2, 1 is going to be, as we had seen earlier, minus times E2 dot I1. We take the inner product and we get the value of I2, 1. Proceeding further, we have to normalize it. In normalization, we have already found a very simple rule for that. It's here. And so your scaling factor comes out to be root of 59 by 6. So you have your I2 vector like this. Now you have found I1 and I2, and the span of this is same as E1 and E2. Correct? They're representing the same vector space. They will span the same vector space. Now, similarly, we can obtain I3 in the same fashion. Okay. So, as you can see, this is highly programmable. So, you can, if you're given, of course, it's a tedious calculation that we have done here, but we don't have to do it by hand. We can use a program to do it for us, a computer program to do it for us. So, if you have access to a laptop or something, then you may want to sort of try to write programs in C, Fortran, C++, Python, Julia, MATLAB, Mathematica, R, whichever language you like or prefer, or you want to learn, whichever language. So you can write your programs in. I cannot give this as an assignment because some of you might not have access to laptops right now. So we'll just, if you have, then you may want to try it like this. You can, but what I want to emphasize upon is this is, and you have what we have found, what we have done is we have written an algorithm. So for any given vector set of vectors, you can construct from that an orthogonal basis. We can, and this process is called Gram-Schmidt orthogonalization process. Now, can we have a similar process for functions? Can we have this kind of a similar kind of orthogonalization process for functions, right? So we'll take up an example and try to do that. So as we have discussed earlier, we can define inner product spaces for functions as well, right? So, and that is essentially an infinite dimensional inner product space. That's what it will be, the function spaces. So let's define. So of course, we have to define this quantity inner product which satisfies all the properties that an inner product function should satisfy. And you can check that this way of defining by using an integral satisfies all the properties that we have listed down for an inner product space. Moving forward, let's take two functions from that vector space, and they will can denote it by f comma g with brackets or f dot g in this fashion, and that is defined by doing an integration of f and g with limits a to b. This is just a definition that we're using. Okay, so this is for functions. The inner product space that we're defining is for functions that are defined over the interval a comma b. So they are not defined for any real values that you might pick or any complex value that you might pick, but we have chosen in an interval. And let's say we are looking at only real valued functions. They take in real values and then they give you real values back. So let's say they are defined over interval a comma b. Uh, for example, let's say if we take a quadratic P2, like polynomial of second degree, that is going to be a quadratic vector space, then a polynomial vector space, then the basis, a general most common basis that you will be using is 1x x square. Now, using this as the vectors, you can define any function, a quadratic function, as ax square bx plus c. Correct? Let's call it c dot 1. So you can use this as the basis to define. Now let's check if this basis is actually an orthogonal basis. Before that, we'll have to, of course, define the inner product. And as we had defined earlier, the limits are given as -1 to 1. A is -1, B is 1. And let's say we try to do this calculation here. Let's say we take 1 and x and integrate. Okay, from -1 to 1, we get a value x squared by 2 minus 1 to 1, and which is 0. So we can say 1 and x are orthogonal. Okay, that's what we get. So 1 and x are orthogonal. Fine. Let's check if 1 and x square are orthogonal. So -1 to 1, 1 dot x square dx, you get x cubed by 3, and you take this value from -1 to 1, and you end up getting 1 by 3 minus of -1 by 3, so you'll get 2 by 3. Correct? Now you don't get a 0, so that means 1 and x square are not orthogonal. Okay, that's what it means. Now this is highly dependent on the vector space, the inner product definition for a given vector space that you choose. Okay, we have, for functions especially, the way we have defined it, it is strongly dependent on whether we define our inner product f and g as just in the limits -1 to 1 f multiplied by g. Let's say in a more neater fashion, let's write this as fx into g of x and dx. If that's the way we define it, we get something. If we define it slightly differently, we can define it like, for example, -1 to 1, and we can use a weight function for this. We can say fx into gx into some other function wx, which is uniform for all the function that you will choose. So we define this special function, and if we do that, the concept, the meaning of orthogonality would change, right? So that's about it, right? So that you have to keep in mind that this is with respect to a given definition of an inner product, and you can define inner product in multiple ways. All right, so now as we see that this basis that we've chosen is not orthogonal for the chosen inner product space, inner product definition. So this is not orthogonal basis. Let's define the norm. for vector 1, because we want to now do a procedure of Gram-Schmidt orthogonalization. So we'll have to normalize the thing. So norm of 1 would be 1.1 dx, which is going to give you 2, which is norm 1 square. So norm 1 is essentially under root of 2. Correct? Now we can define a unit vector q1x as 1 by norm of 1, which is 1 by root 2. Correct? Now we take dot product between 1 and x, and it turns out this is, now we have gotten the first vector now. Okay, so this is like writing the way we were writing e1 as i1. So same way we have now this i1 is essentially your q1. Okay, now we write we want to find i2. So let's pick x. So here we are writing i2. We can write i2 as e2 plus i2 i1. Correct? So we'll follow the same procedure here. We'll try to find e2 dot i1, and that's going to be like 1 comma x, and that gives you a 0. And then so it turns out that your xi21 is nothing but a 0, because 1 and x are already orthogonal. Now we find, because we have to normalize, so we find the norm of x and x, and it turns out to be 2 by 3. Norm square is that. So you have q2x can define as x by norm of x, and then you get this. So you have found I2. So now you have E1 comma E2 is equal to I1 dot comma I2 span of this, right? So you have, similarly you have here, I mean, just to draw correspondence between the two concepts, Q1 and Q2, the span is essentially your 1 and x. 1 by root 2 and x is multiplied by root 3 by 2, right? So that's what this is. Correct? Now we want to find the third vector, q3. For that, we take the inner product between 1 and x square, and you get 2 by 3, which is not 0. It's not orthogonal clearly. And so 1 and x square are not orthogonal, as we had seen earlier. And so now we use this Gram-Schmidt orthogonalization. So q3 is written as the vector e3 plus xi 31 e1 and xi32 e2, and then you have to divide it by the norm of that thing. So xi31 is xi31, as we had seen earlier, is ie3 dot i1, and that's what we're doing here. E3 is x square, and i1 is 1 by root 2. You get minus root 2 by 3 doing this procedure. And to find xi32, you will have to do minus e3 dot i2, and it turns out it is 0 because x and x square are orthogonal. Correct? Now your normalization factor reduces to only 1 to be added to x square. Do that, you end up getting some factor like, and do the integration and take the under root, you get a factor 1 by 3 root of 8 by 5. Okay, this gives us q3. It has this form of 3x squared minus 1. Right, so now 1x, now the new set of vectors that you have gotten for this polynomial space is 1x. So we are looking at a P2 space, which is essentially given by the span of these vectors, correct? Polynomial space of degree 2, which is quadratic space, is given by the span of these three vectors, right? Now we have, for the same space, we have gotten these three new vectors. Okay. You can of course expand to P3, P4, P5, and so if you go in this fashion, what you're getting here is the new vectors that you keep getting 1x, 3x square minus 1. This is plus the next one, next one that you keep getting are nothing, it turns out, but they are legendary polynomials, okay, which have this spatial property of orthogonal being orthogonal minus 1 to 1. Let's say legendary polynomial 1 and legendary polynomial 2, they are, it's going to be 0. Okay, so this is the property of legendary polynomials, that the inner product for these legendary polynomials is 0. Legendary polynomials are solutions of the following ODE. This ODE, which is you must have seen in many engineering problems it turns up, and so it is a useful equation to know. Now for n equal to 0, the series solution you will get is essentially 1. N equal to 1, you get x. And for n equal to 2, you will get 3x squared minus 1. Okay, which forms a set of legendary polynomials. Okay. Now, if we do not normalize, I mean, that's what we had written earlier. So the normally legendary polynomials that you will come across, they will not be in the normalized factor, but they still satisfy the orthogonality property. So it's going to be, they're going to be like this. This is very useful to know. So you can solve for P3 by putting n equal to 3 in the ODE. Okay, but there is another way. Now we know that we can use a Gram-Schmidt process, and we'll use it on this set, and using this also we can get P3. Okay, so this is an easy way of solving that ODE in a way. This is just because we know that it satisfies that additional inner, for that particular definition of inner product, you get that kind of an orthogonal conditions. There is another set of interesting polynomials which is called Chebyshev polynomials, and they are defined. The inner product for them is if you use the weight function 1 by root of 1 minus x square. If you define your inner product in this fashion, then and you start with the same initial basis as 1 x square. Let's say we just stop here at this for the P2 space. Okay. And then you want to find the corresponding T0, T1, and T2, the first three Chebyshev polynomials. And it has been given that the inner product that you're using for which they are orthogonal is given by this. Now we can use a Gram-Schmidt orthogonalization process, and on this basis to get these three. So that will be your homework to get these Chebyshev polynomials in this fashion. So we'll stop here today. Next time we'll talk about linear transformations.